Hey guys. It's gonna be fun.
Yeah.
It's gonna be fun.
You're now audible.
Yeah, I was gonna say, yeah, it's gonna be fun.
So,
Okay.
have a seat, folks, and I'll just get things underway.
So I guess, s'il y a des gens qui veulent demander des questions françaises,
Oui.
allez-y. Watch that iPhone.
Hello, Mark. Shaky.
Annoying, isn't it?
As long as we don't move.
Okay, I don't have a mic, everybody, so I'm using my outdoor voice. We're starting our first plenary today, Aviation Autonomy. We have 5 panelists. The chair is Marc Alexander from NRC. And I don't think I want to take any more of your time. We're a little behind getting underway today, which is fine. We can keep doing that for the rest of the day. We're under no panic. But I think it would be just as well for me to lead things over to the panel. Marc is on my far right, on your left. And perhaps, well, the panelists are introduced in your program, of which you have a copy, most of you. And so I'll leave it over to Marc now.
Hello everyone. Sorry for the late start. Looked like we had to get a robot to put in some chairs for us. But anyway, it's wonderful to have you all here. It's an amazing time in the aviation industry, as you know. Whether you're talking fixed wing, rotary wing, drone technology, it's a spectacular time, especially for young people. How many students do we have here? Put up your hands. Holy smoke. So, there you go. Pay attention, because there's so much opportunity in this presentation, in the technology, in the domain. If you're starting your career, this would be a wonderful place to start. So pay attention, take notes, record. This will be great for all of you. So the topic is human-centric aviation autonomy. The idea that in the coming years, and even right now, we're integrating full-scale unmanned aircraft, drones into the aviation environment. These technologies are going to be teamed with people, with humans. And they're also going to be we're also going to potentially operate these systems autonomously, monitored by humans, of course, monitored by machines. So it's a fascinating use case. In terms of the discussion today, I've got 5 of my colleagues here from industry, research, academia, government research, military regulation. And we're going to have an interesting discussion on the topics of artificial intelligence and autonomy. How to regulate it, how to develop it, how to select it, what are some of the challenges and issues associated with it. And obviously for the students, how do I land that first job? That's not going to be paying me any money. So I guess in terms of the overall layout of the panel, basically for about 90 minutes, we'll have the panel will execute. In terms of the layout, I'll give about a 10-minute discussion, just to situate you in terms of the autonomy space, in terms of regulations, technology, some of the public domain aspects, etc. And then we'll have a panel specialist review where each of the panelists will provide an overview of their particular area. And then I will have a moderated panel interaction, about 30 minutes, where I'll interact with them, asking questions and grilling them, making them sweat. And then we'll have the audience interaction where you can ask them questions. So if you would, prepare your questions, and at the end of the session, I'll have an interaction for you where you can interact with the panel members. So how about, I guess I should introduce them. That would be a good idea. So Jeremy Wang is a Canadian aerospace engineer. He has a doctorate from the University of Waterloo 8 years experience in aerial drone remote robotics and applications. He served as CTO of a major drone operating company and set up a systems design deployment division. He co-founded cargo aircraft startup Ribbit, which develops self-flying airplanes and enables pilotless fleet system applications and organizations. And Ribbit is growing. They have several milestones. Their autonomous demonstrator executed hands-off flights between 2 Canadian airports. In terms of qualification, they received an SFOC to operate that air vehicle from Transport Canada. In terms of growth, they have engagements with 6 major clients and recently won a federal government testing contract. Welcome, Jeremy. My colleague, Derek Duff Gowanlock, is next to him. We work together at the Flight Research Laboratory of the National Research Council here in Ottawa. Derek is a qualified flight test engineer, very experienced with 25 years experience in flight test certification, working on diverse programs and projects for the Royal Canadian Air Force. He's a graduate from the National Test Pilot School. And then since joining the National Research Council, Derek has managed the Canadian Vertical Lift Autonomy Demonstration Project, as well as the Flight Autonomy Research Thrust under the Aero Division, Integrated Air Mobility at the NRC. Welcome, Derek.
Thanks.
Philippe, Doyon-Poulin is an assistant professor at Département de Mathématiques et Ingénierie Industrielle à Montréal, Polytechnique de Montréal. He performs research in aviation, human factors, error prevention, automated systems decision-making, and he has expertise in certification compliance in areas of flight deck usability and pilot error. Welcome. Welcome. Benoit, Ouellette, the senior technical expert at Bombardier, has a focus on aircraft flight deck avionics systems, 20 years of expertise in the area. And he has a specialist focus on human-centered design, human-machine interface concepts. His key commercial projects are associated with flight deck contributions from design to certification, and those associate with aircraft that you'll be familiar with. Some of you will be familiar with the C-Series and the Global 7500. Welcome.
Thank you.
And Major Yann Moffett. Welcome, Yann. Yann is also a military expert, 25 years of career expertise in the Canadian Forces. He has a number of lead and specialist roles contributing to the CF-18 Weapon System Management Program, or Weapon System Management, Software Techniques, Avionics Systems, Directorate of Technical Airworthiness and Engineering Support. He's currently a public servant supporting RCF fleets in system safety and software team, and a software team lead. So we have, welcome, we have an exceptional team here today. I was going to say, if any of you wanted to ask questions in French between Philippe, myself, and Benoit, we can tackle those questions. So, where to begin? I guess the first part of the presentation or the panel is going to be just situating you in terms of where we are in terms of autonomy. Cyber-physical system. A computerized system or a computer-based system that is controlled or monitored by algorithms. We hear this notion quite a lot in the vertical lift industry. I'm not really sure if we hear it a lot in the fixed-wing industry. But this is the environment that we find ourselves in. Aircraft that are not simply rotors and wings and aerodynamic systems and structures, but are fully integrated with sensors, computing systems, flight control systems that have adaptive capabilities, moving towards the idea of being autonomous, possessing artificial intelligence, possessing flight systems intelligence. This is the playground that we find ourselves in as aerospace engineers, as students wanting to study, as test pilots coming in and testing the systems, as researchers, as a startup company who is actually planning on developing these systems so that they can support our country, the social infrastructure in our country. Very, very important. And these technologies are going to enable us to enhance capabilities. So we look at some of these capabilities or these capability sets: mission task execution, environmental robustness, productivity, redundancy, assistance, life cycle extension, vehicle design. We hope that, and we desire that, autonomy will enable us to improve vehicles in some of these areas. Now, to give you sort of a framework or to situate you in terms of where we are, I'll discuss a little bit about projects and programs and initiatives worldwide in the regulatory domain, in the technology development, demonstration domain, and a bit in the social area. We'll look at some professional organizations, the public, how the public is getting involved in this area. So in the regulatory domain, Transport Canada is heavily involved. They're heavily involved with the CVLAD, NRC Autonomy program, interacting with us, the researchers, where they're looking at trying to understand certification processes of technology in this novel field. They provided an SFOC to Ribbit, enabling them to operate their autonomous aircraft in a test capability throughout Canada. Developing policy and regulations for beyond visual line of sight, collaborating with Drone Advisory Committee and ICAO, and importantly here, everyone is developing technology, but we need to develop it collaboratively. We need to make sure that technology is viable as an operational set throughout the world and be able to collaborate with other organizations. So in terms of air mobility, they're doing that through ICAO. FAA, as you know, is heavily involved. These are just some of the areas: drafting urban air mobility concept of operations. The last one, involvement in UAM research and technology demonstration. Probably most important one is establishment of policies and a policy and innovation division. So FAA actually stood up its own division where they could look at advanced technologies, autonomy, machine learning, artificial intelligence, all of these technologies. They want to be able to help certify it. They want to do that just as much as Transport Canada does. So they actually set up an entire division to do that. European Union, IASC, they have an artificial intelligence roadmap, and you can see some of the areas here: air mobility, security, safety, trustworthiness. I have several roadmaps here, and you'll see the same theme throughout. The desire to use the technology for a particular nation's benefit. Vehicular development. I found what's really interesting now is if you look at the vehicle design requirements, you see autonomy and artificial intelligence actually in the requirements. Some of the military members might be familiar with this if they've worked on the Future Vertical Lift and are looking at that. So U.S. Future Vertical Lift, Future Attack Reconnaissance Aircraft, FARA, and Future Long Range Assault Aircraft, FLRAA, are rotorcraft, runway independent aircraft, capable of vertical takeoff and landing. The objective here is to replace aging military aircraft and provide novel capabilities. Full-scale systems, optionally piloted capabilities flow into Future Vertical Lift, but also the NATO Next Generation Rotorcraft Capability, which is an EU program, and they're looking at the same thing, replacing helicopters over the next 30 to 40 years. The requirements are there. Medium to small autonomous platforms and U.S. launched effects, air launched effects, where a vertical lift aircraft or a fixed-wing aircraft will have a drone, and they'll launch that drone beyond a visual line of sight to gather information, teaming that vehicle with the mother aircraft. These are some of the other programs that the U.S. military and the Canadian military is interested in. In the fixed-wing area, some of you may have heard of the Collaborative Combat Aircraft Loyal Wingman program. So this is another program where an air vehicle will be teamed with an aircraft such as the F-18 or the F-35 to support that aircraft, to protect that aircraft, et cetera. DND. DND also has its roadmap, a strategic roadmap, and in it says autonomous and uncrewed systems, as well as AI, machine learning, cloud computing, et cetera, are innovative technologies that the RCF must leverage in terms of its operational advantage. So the military may not be planning to purchase a future vertical lift aircraft, but they know the strategic value of all those technologies, and they're learning. They're using other government agencies, academia, et cetera, to learn about those technologies, technology demonstration programs, et cetera. Professional societies and consortia. These are influencing development, regulations, and implementation of AIA. So Canadian Air Mobility Ecosystem. Well, what am I doing? I should start with CASI. I mean, the idea that we could have this plenary session put together on such short notice, and all of you here for the first event indicates there's a significant interest in this, and this is just going to grow. Canadian Air Mobility Ecosystem, CREAC in Quebec, they have a roadmap as well, and you can see some of the areas: economics, social acceptability, aerospace management, security, similar to the other roadmaps. The Vertical Flight Society advocates for vertical lift research and development, my area, and some of the programs that you saw, Future Vertical Lift, as well as urban air mobility on the civil side are programs that they advocate for. Big one is the Society of Automotive Engineers, who develop standards. So some of the standards and programs that they have to develop these standards in terms of artificial intelligence include the Artificial Intelligence Aviation Joint International Committee. And then AIAA also has advocacy, and you can see their critical areas are artificial intelligence, advanced mobility, and cybersecurity, robotics. So you can see how professional societies, lower end of the, I guess you'd say necessarily the technology development spectrum, are getting involved and advocating to bring this technology through. In the research domain, well, always probably this is the most important area. It's my view that we're at this stage now where we have all the key components, or we have most of the key components, I should say, to enable development of the initial structures, the initial capabilities of an AIA flight system. And I believe we're gonna do that through technology demonstration programs where the military may request a knowledge generation opportunity using government facilities and academia to flight test an aircraft that has autonomous capabilities. And this is what we're doing through the CV-LAD program, supporting the military, supporting other government departments, and understanding what this technology is and how to use it. DARPA is the U.S. government research organization, is a U.S. government research organization, and they're doing the same thing. One helicopter program was called the Autonomous Aerial Cargo Utility System, which was basically a payload system integrated into a variety of helicopters like the K-MAX, the UH-1H Bell 205, and other platforms. Lockheed Martin Sikorsky has an aircraft that they're doing research with, and Near Earth Autonomy is an SME with significant experience in perception and systems. So a lot of technology development through that space. Civil fixed wing, Airbus, for example, is developing technology, Dragonfly and ATOL for pilot assistance, automated takeoffs, automated landings of major transport aircraft. So fascinating technology. Civil fixed wing maintenance, Bombardier is investing in the artificial intelligence ecosystem, and recently was at several conferences in Europe, European Rotorcraft Forum, and NATO conferences where predictive analytics is very big with industry. The idea that you can take all the data emanating from these aircraft, emanating from sensors over years, analyze that data and understand structural issues, failure issues, training issues, et cetera. And then civil UAM, I mentioned this before, a number of organizations involved in developing technologies and researching in that domain. So, without further ado, I want to grill these gentlemen. So, enterprise, government research, academic research, industry, regulatory domain. We have a broad representation here of specialists and people. From the student perspective, you know, all of us started out just like you. You know, we had interests and we had passions, and we took those passions forward. So as we discuss, pay attention, you'll hear keys of opportunity and things that you might be interested, things that you're already working on that you can pull forward into research projects or career start ideas and other things. So, thought we would start with Jeremy, and Jeremy's going to discuss his activities at Ribbit. Ribbit?
I think I can take the clicker from you. And then,
Is it on?
might be. No, I think we have to switch to the. There we go. Okay. Is that? Here, I'll come around.
Yeah, I think that's it there.
Thanks. Okay, awesome. So I'll try and keep us on track here, and I'll basically just jump right into it. From February of 2021 up until about middle of 2022, we took a two-seater plane, stripped out the back seat, and made it fly by itself. And in the next few minutes, I'm going to summarize a little bit of what that work looks like and paint a bit of a view of what's going to happen in the future as well. But before we get into that, and I've asked some of this, I've asked this question at previous presentations, so if you already know the answer to this, don't say it out loud, okay? But if you were to take a guess, how much do you think groceries would cost as a percentage of your after-tax income if you lived in, say, one of these remote communities in northern Canada versus, say, here in Ottawa or in a bigger city? And please, feel free to shout out the answer that you think it is. It is pretty expensive. Okay, so 70 and 45. Okay, interesting. Any other takers? Come on, don't make this awkward for me. Somebody, anybody. 50-20. Okay, interesting. Okay, so we have a pretty pessimistic view, and it's appropriate. It is appropriate. So here's the interesting part. If you look at Statistics Canada data, and I have to caveat that there is undersampling in a lot of remote communities because there's not a lot of incentive to participate in these censuses, it's about 25% versus 10%. Now this is based on the 2016 or 2021 census data. So it's actually gotten worse since then. And on top of that, this was during a time when there was stimulus funding from the pandemic. So if you actually take some of the older data, it's closer to 43% in remote communities, and then about 10 to 20% for most of Canada. So it's quite severe in northern areas. And as you might expect, the reason why I'm bringing this up is because affordability is very closely linked to transportation. There's a lack of year-round road access. The price of transportation is a challenge, but also the reliability of accessing flights on the schedule that are listed is another big challenge. And so Ribbit was founded in 2020 in the middle of the pandemic, motivated by this. I mean, our team consists of aerospace engineers and pilots that are obviously very passionate about this technology, but really from a societal perspective, our mission is to try and make air transportation more accessible to everybody, starting with the hardest to reach areas of the world, so rural, remote, and coastal communities. In terms of what this demonstrator does today, we've broken it down into a number of high-level phases and then kind of sub-phases inside there. So from an engineering perspective, it operates more or less like a finite state machine for all practical purposes, where you have a taxi state, takeoff state, en route, and landing state, and within those you have substates. So in the taxi state, for the most part, the aircraft is driving or taxiing along the trajectory that's been generated, and it'll wait at certain predetermined points for pilot command to proceed. So for example, if we're approaching a runway to cross, it'll by default stop at a hold short line and wait for the pilot to say, okay, it's clear to proceed, and then proceed. But otherwise, it's driving on its own. Takeoff, roll, rotate, climb, pretty standard things. En route, there's a cruising state where it will do kind of the climbs, descents, holding kind of steady level flying. And then there's also what's called a DAA state, or a detect and avoid state. That is the equivalent of kind of collision avoidance, or TCAS, on commercial aviation today, where if it notices an intruder aircraft, it can automatically generate a collision avoidance maneuver to stay clear of that aircraft and then resume the mission afterwards. And then landing is also pretty straightforward. So in terms of where people are involved, or where the pilot is involved, like I mentioned earlier, during the taxi state, stops at intersections and crossings, waits for pilot input to proceed. During the takeoff state, pilot gets involved if something bad happens. So if you need to do an aborted takeoff or a rejected takeoff, that can either be triggered manually by the pilot in command, or it can be done automatically based on kinematics if the plane realizes it's running out of runway. In the air, it gets interesting. Human perception, we've noticed, is actually quite a remarkable thing. And if you try and use off-the-shelf sensors today to try and detect other aircraft, let's say below 2,000, 3,000 feet off the ground, you get a lot of reflections, a lot of noise. You have to filter out aircraft from the background of forest or ground. If it's radar, you get reflections off of metal objects. It can be quite challenging to use. And so we do rely on a safety pilot inside the plane for that perception function close to the ground. And then likewise for landing, it can either be avoided by kinematics if we realize that we are drifting too far off the glide slope, or by pilot command again. And that's essentially the extent of human involvement plus voice communication. So we still rely on a safety pilot to talk over the VHF radio to other airspace users, be it ATC, flight following, or other aircraft. So at a high level, this is what it looks like. We're kind of at this level 3, I would say, in terms of the typical autonomous frameworks that you find out there, where a nominal gate-to-gate flight is done by the aircraft. There is some basic mission adaptation where you have collision avoidance that will manipulate your trajectory to stay well clear. But we always want the autopilot system to be overrideable. And likewise, we always want the safety pilot to be able to do that override if it's necessary. On the other hand, that safety pilot inside the aircraft is primarily supervising across all phases of flight, with greater involvement closer to the ground, as you can probably tell from the taxiing and the rejected and aborted takeoff or landings. And that's about it that I'll say in terms of slides. We'll jump right into what it looks like. So with that in mind, we do all of our testing out of CZBA, which is Burlington Executive Air Park. It's a really nice small private aerodrome just west of Toronto that isn't so busy. And during the taxi state, the aircraft basically follows the taxiways and does what it needs to. For those of you who know how to fly a plane, you'll know that I could be lying to you about the way that this plane is driving around. You can't actually see the rudder pedals moving. So you'll have to take my word for it that this is actually the plane that's doing it. But the one thing I'll just like to highlight is if you look at the stick on this turn, you'll see that the stick actually changes direction. And that's because with aircraft taxiing on the ground, especially small aircraft, you have to angle the ailerons and the elevator depending on the direction of the wind, so that you're kind of counteracting the aerodynamic effects of wind as you're changing directions from the ground. That's a very important feature. The other part is that aircraft don't drive in the same way that we drive a vehicle. Typically when you're driving your car, you might hit the gas pedal a bunch. Normally, general aviation pilots will kind of set the throttle at a particular setting and then brake to control speed, and that's reflected in the control laws for this system. So that's taxiing. The way that this works is the pilot will input what the meteorological forecast says for where the wind is that day, and as the aircraft starts moving along, the air data boom on the front will actually determine the correct wind speed and direction as it actually is, and then determine what the active runway is. The pilot can also override that if based on VHF command or VHF radio, kind of talking to other pilots, it's actually a different runway. This is now takeoff. So this is again at Burlington Airpark. And on this particular day, we had a little bit of wind and a little bit of rain. But again, I'll just play the video. So you'll see that the pilot lets go of the stick there. Same deal, the stick is angled towards the right because we have a small crosswind from the right. You can see throttle that advanced left on the left-hand side there. And as the plane reaches the speed necessary for rotation, the stick pulls back. And as soon as it cocks into the air, it switches control laws. There's a lot of blending and fading considerations that go into that, so you don't have a sudden discrete injection into that system. And if you look very carefully, you'll also see that the aircraft has yawed slightly. So that will be referred to as crabbing. You crab into the wind to counteract the effective wind. And that way you can maintain the runway center line, an extended runway center line, as you continue climbing and entering the circuit. And from this point onwards, the plane is continuing to do everything by itself. The other interesting observation is you can always tell what phases of flights the pilot has the most confidence in, because their left hand currently is hovering over the disengage switch at the moment. So if anything happens during these flight tests that requires manual intervention, you flick that disengage switch, it automatically powers off all the servos that are connected, and they're electromagnetically clutched. So by default, if there is a power failure anyway, it'll disengage, and then you resume manual control. Now we're in the air. So this clip is from actually a set of recent flights we did in northeastern Ontario between Cochrane and Iroquois Falls, about 700 kilometers north of Toronto, where we did the first gate-to-gate flights between two airports without any human intervention whatsoever. So from takeoff to in-flight, back to landing, and then we did that about 6 times, or 3 round trips in total between those two airports. In the air, things are pretty benign. You can see the pilot has his hands back on his thighs. If you look carefully, you'll see the purple trajectory there. And again, because there is wind on this particular day, the aircraft stays crabbed as it's flying through. And now comes to the most exciting part, which is landing. I don't know if I can actually pause here, so I'll give it. Can I do it? No, okay, it's not going to work. So if you caught at the very beginning, on landing at Cochrane, we actually had a pretty high crosswind, about 20 knot straight crosswind. So much so that at the very start of this clip, you can actually see the runway we're trying to land at out the left-hand window. And so as the plane comes in for landing, it's trying to track this glide slope, aiming for a target point on the runway. We typically set that target point a little bit further downstream from where the actual target would be if you were a human pilot, because we want to give extra margin if we need to do a short landing. But nevertheless, it's tracking this glide slope. On this particular day, it was a little bit bumpy, like I said, 20 knot straight crosswind. The aircraft is rated to that. So basically, in this particular flight test, we're trying to see if we can maintain the flight envelope of the original aircraft prior to modification. As it's coming in, we have both GPS and a laser altimeter that's fusing the kind of the height above ground to within a couple centimeters. And you can see here we have very similar displays to what you'd expect on an ILS system for horizontal and vertical deviation. 15 feet off the ground, aircraft starts to flare, power gets cut. We're now just hovering and bleeding airspeed a little bit. And you'll see the mains come down first, and then the nose. Aircraft realizes it's on the ground, and it's basically holding center line now, and it transitions back to taxi later on. As of today, we've done about 200 or so hours of hands-free flights, so taxiing, taking off, flying around, landing between Burlington and up north. As mentioned already by Marc, we have a Special Flight Operations Certificate, or an SFOC from Transport Canada. It kind of functions like an exemption or a waiver mechanism for systems that have been shown to work under certain operational environments that are risk mitigated. And as we look to the future, these are the kinds of questions that we're looking at. If you think about it as a controls problem, the way that we've approached this is we started from the innermost loop of the system and we've started working our way out. So basic fly-by-wire, basic control laws, basic navigation, all of that's there. A lot of the questions that we're trying to address now have to do with perception, so noticing other objects and avoiding them. And again, when we looked at off-the-shelf sensors today, whether it's computer vision, whether it's radar, whether it's LiDAR, and LiDAR, because it's so short range, has very limited use in the air. These are the three things that kind of keep coming up, is being able to achieve the necessary range and field of view is a challenge. Being able to achieve robustness across different weather conditions, different lighting conditions, different heights above ground, and the noise profiles, background noise profiles, all of those are big challenges. And then this challenge between sensitivity and specificity. Is anybody here from Transport Canada? Just by show of hands? No? Okay, good. So I can say this then. Okay. So there's a guidance document that was released, AC 903, Advisory Circular 903, that's for Special Flight Operations Certificates. And if you look into the details of it, they have these requirements for accuracy of detecting other aircraft. And I think the most stringent requirement today is about 90% accuracy. Now, if you're a responsible engineer, you'll know that accuracy can be defined in many ways. You have false positives, false negatives, true negatives. As of today, the guidance document doesn't specify kind of what it looks like across sensitivity versus specificity is essentially what I'm trying to get to. But these are the kinds of areas that need to be addressed as we move forward. Luckily, there's some new means of compliance that are coming out very soon. But when the document was first released a few years ago, that was something that industry had pointed out. On the behavioral planning side, I'm trying to get at navigation. So this is trying to achieve more fluid, human-like behavior and being able to adapt the trajectory as you're flying. States and transitions is a big one. So for example, the way you would do collision avoidance when you're in the circuit around an airport is very different from the way you do collision avoidance when you're en route between two airports. If you're in the circuit around an airport, you're following other traffic. If you get too close to another plane, chances are you're not going to suddenly make a heading change or an altitude change. You have to stay 1,000 feet above that above the aerodrome, and you want to stay in line with the other aircraft. On the other hand, if you're en route, you have more freedom to make those changes as you see fit. And knowing where that divide ends, when one starts, one ends and the other begins, and making those transitions fluid is a challenge. And more broadly speaking, that aspect of adaptation is a big thing. We have a notorious reputation at Burlington Airport for messing up other people's circuits, and that's because of how rigid the circuits can be sometimes. The last part I'll just touch on is certification. Machine learning is a new category of software that currently there's a lot of guidance material still being developed for that. And certainly while we're in this transition state where you still have a safety pilot, as well as an autonomous system, there are new failure modes that you can introduce where you need to be able to know when to engage versus disengage safely. This is our path to market. At the current stage, we're basically at the stage of setting up an air taxi operation that will be going live middle of next year. Initially, those aircraft will be piloted by a person on board, and gradually over time, we'll be working with TC or Transport Canada to phase out that onboard pilot to a remote pilot that's monitoring. And the last thing I'll just say is, going back to the original mission of why we started this company is to make aviation or air transportation more accessible. The World Bank puts out a report every few years looking at travel time to the nearest major city across all modes of transport. And as you can tell from this, the darker areas are the areas that require longer travel times. And northern Canada, Alaska, lots of continental regions of South America and Africa, Central Australia, island nations, there are still a lot of areas of the world that lack connectivity. I think probably the most striking conversation we had with the community in the north was that they had internet access, they had Starlink, they could watch Netflix, but they couldn't get their food at an affordable price and on time. And that's something we'd like to change. So thanks for having me here today, and I'll pass it to Duff for the next one.
Yeah, so I guess I'll roll next. Yes, my name is Duff Gowanlock. I'm a research flight test engineer at the Flight Research Lab, and it's a great pleasure to be here and represent quite a large research team back at the NRC who've been working on the flight autonomy problem, a few of which are here in the crowd. And as Marc has those hard questions, I'll be sure to defer them to the experts that are in the room. So our efforts around flight autonomy really go back about 50 years when we started doing fly-by-wire developments on a Bell 47 in an analog fashion back in the 60s. Over the years, we've incremented that capability up into the Bell 412 Advanced Systems Research Aircraft. And in parallel, we've conducted aviation human factors research, more than a decade of detect and avoid research, technology development, and dozens of small-scale, large-scale drone activities. And so as we sort of looked at that body of work in total, we embarked upon a project called the Canadian Vertical Lift Autonomy Demonstration, or CVLAD, as an effort to get an initial research and development capability to support research, as well as demonstrate technology. And so we developed an autonomy core, discrete event system, decision-making for mode state changes, logic, trajectory state changes, et cetera. Developed functionality around perception, understanding our place within the world and what the world looked like around us. Trajectory planning, how do we find our way through that? How do we interface that trajectory and manifest the trajectory in real life? And then, of course, developing a mechanism for human interface so that the human that's supervising the system can understand what the machine is intending to do. This project's been going on for a number of years. We had our first full autonomous flight from takeoff through to landing back in March 2022. And then recently, earlier this year, we deployed down south to do some austere environment testing, which actually Brian Carruthers and I will be talking about a little bit later this afternoon. Looking forward to that. So this activity was sort of the first foothold, if you will, into autonomy within Canada. And now we're advancing in a new project, which we had been calling CAFES. New acronym I think we're going for is ASCEND, Advanced Autonomous Flight Systems for Challenging Environments, Development and Demonstration. And essentially what we want to do is expand collaboration, expand investment in all of these key pillar areas of flight autonomous systems to further advance the technology within Canada. And so in that initial R&D capability, we had a number of collaborators, notably National Defense, major supporter of the activity, but some academic and industry collaborators north of the border and south of the border. As we look into the new advanced development project, we're looking to 4 or 5 times size that to increase and enable much more significant academic engagement for research, as well as industry engagement in Canada overall. So that's sort of our big picture roadmap, where we're trying to go, where we're at, what's coming next. Just a few words on CVLAD itself, what are we doing currently? And so the objectives of that project are to demonstrate kit-based autonomous flight technology on the Bell 412. We're particularly interested in workload as we look to reduce crew through the application of supervised autonomy. We want to demonstrate operational capability enhancement, degraded visual environments, degraded GPS. And we want to inform concept development, and that's sort of part of the military angle on this project, as well as regulatory development. And in that way, we have a working group with Transport Canada and DTAES. And in that working group, we're looking at a number of different Canadian-specific research questions that the regulators could use the answers for to help shape the formulation of regulations to enable early adoption of the technology. And so a very important piece of the project work there. And then fundamentally in CVLAD, and sort of part of that build-up from that initial capability that I just spoke about to a more advanced functionality, is we wanted to create a backbone strategic autonomy test and development platform, which is the Bell 412 with a full suite of autonomy capabilities and services integrated with it, which then we can collaborate in future with industry and academic partners, swap out services, swap in services, develop and demonstrate, investigate, study all different types of technologies around autonomy. In terms of sort of just the very high level capabilities, on the machine side, the autonomous agent, it's autonomous from takeoff to landing. We have a digital supervisor, which is a discrete event system, which controls the key decisions, trajectory changes, mode changes, et cetera. We have a system that does landing zone evaluation, and in fact, including a neural network-based algorithm, and that's the only AI application that we've introduced in CVLAD. Everything else is sort of classical methodologies. We have ground-based obstacle avoidance technologies, cooperative detect and avoid functionality, abilities to operate integrated environments to a degree, and importantly, we have this foundation to support human autonomy research, which is really all about the human-centric perspective of the implication of increased automation. On the human side, the human's there to supervise the autonomy, and so that's their key role. They define the intent and the goal, and within that, we have a couple of concepts that we're sort of introducing, discussing. One is a concept around level of aggression. What degree of aggression does the machine, or is the machine allowed to use to achieve those goals and intents? And then the contract, which is the boundary, the limit of authority that we afford the machine to execute or achieve that goal. That can be thought about in sort of a tube in space kind of context, but there's other dimensions to it as well. And fundamentally, it sets the expectation agreement between the autonomous agent and the pilot who's sending the mission. The human also has in our system high level, mid-level, and low level ways to intervene. So high level being sort of changes in goals, low level getting right on the sticks. And we have, as a feature of our fly-by-wire helicopter integration, we also have a fly-by-wire human on board a human that's monitoring the fly-by-wire system on board. And that's an artifact of the fact that our fly-by-wire system is single string. It's a research system in and of itself. And so we require safety backup on that front. And again, that whole set of high-level capabilities provides us an ability to conduct our human autonomy teaming research now and into the future. So this is a quick video of some of the flying we did when we deployed down to Yuma, sort of desert, mountainous environment. Just to give a flavor of where we're at with the technologies. This is now about 8 months old in terms of what the technology's at, so we continue to progress. In this case, we're going to see a ring mission. We take off from an airbase, fly around an area, and stop at some planned locations. So the mission's been uploaded, and I think that's Brian's finger we're seeing swiping the screen. That transfers control to the autonomous system, and now the helicopter is controlling itself. We see the takeoff, and then the departure on the mission line. We come to our first planned location site, which is a ringed compound or fence or a confined compound. We identified an area of likely landing, safe landing location in the corner, and then we allow the system to scan the area, do landing zone evaluation, and find the optimal location. So once the optimal location's found where that little green ring was, the aircraft then transitions over to that point and lands itself. In this case, it's a gravel pack. It's a great landing spot, a little bit of dust, and we'll talk more about that in our presentation this afternoon. And here we see the helicopter landing itself. So we simulate offloading some cargo, and then the pilot transfers control back to the autonomous system, and the aircraft does a departure and continues on the planned resupply mission. In this case, in this concept, we had an arising mission retasking planned. So we had this simulated tactical operations center reach out to us through a tactical data link, tablet-based in the left seat, and asked us to go to a new location. We interacted through the tablet base with a common operating picture you can see there on the left, sort of text base, and we teamed with a German UAS system and tasked them to go survey the landing location. So they launched their vector drone and flew out and provided us information back. And as a result of that, we introduced a dynamic mission change, uploaded it to the vehicle, and then had the vehicle execute the ad hoc mission. Here you can see as we're just sort of turning into that new mission, and this is sort of how we normally fly. System supervisor in the left, safety pilot in the right, both hands in our laps. And in this case, the intended ad hoc landing location, the point we picked based upon that surveillance information was a convergence in a road. And so that we figured that would be the most likely place to have a safe place to land. We identified that location and then let the system find the optimal place to land in there. You can see a lot of red in the landing zone evaluation. Red is bad, green is good. And that's a lot of the dust effect that we see based upon the sensors that we're using in this demonstration. And again, we'll talk about that from a technical standpoint a little bit later this afternoon. So that's and then of course the helicopter comes into land, of course. See a little bit more of dust. So that's sort of the state of the art where we were about eight months ago. Development continues. And we have another about 8 months left to go in the program, and so we'll be looking to do more demonstrations once the weather improves and the technology is ready to go. So look forward to presenting those results in the future. Just before I wind it up, did want to turn back to those next steps. What do we plan to do next? And so really, this is sort of a one-slide shopping list of different technology areas of interest, as well as research areas. On the human-centric side, the research list is long, as I'm sure you can imagine, so these are just sort of a few that are cherry-picked. But fundamentally, we want to find collaboration with industry and academia to explore these areas, to develop technologies, integrate technologies, technology services, if you will, or autonomy services, if you will, around human interface, teaming technologies, perception, AI-based algorithms. Obviously, that's a big area of interest for us, as well as develop fixed-wing-based capabilities. And we'll see where where we can potentially collaborate. And then look at research on the human-centric research around workload, around controlled transfer, pilot intervention, situational awareness loss, regaining, concepts around not only the human monitoring the autonomous system, but the autonomous system monitoring the human and potentially controlling and helping inform the pilot to aid situational awareness gaining. And then fundamentally trust as well. So many research activities there. And certainly if anybody's interested in discussing any of those further, feel free to grab me or any of the NRC team. And with that, I'll pass it over to, I think, Benoit. Just need to advance to the next slide.
Next slide?
No. Yeah.
Okay.
Can you advance to the last grouping of slides in that PDF? No, keep going. There, keep going.
Perfect.
Back.
Go back. Excellent. Thank you very much. Perfect. So I will talk about a different perspective today, which is Part 25, aircraft design and autonomy. Normally, the larger aircraft is not associated with autonomy. I just want to highlight the possible application of technology, the challenge, and the research and development needs to be able to bring more elements from the research on autonomy for large aircraft. So the autonomy application for large aircraft, Part 25. So Part 25 could be like a commercial aircraft, a Boeing 737, for example, or a business jet.
The first element and the most important element of autonomy, what it can bring to that industry, is being a single pilot operation or reduced crew operation enabler. And if we want to define single pilot operation, is the operation of a large aircraft, Part 25 aircraft, with only one pilot gate to gate to perform the mission. Reduced crew operation is to have one less pilot than you will normally need when you need augmented crew for long range flight. So if you will need 3 pilots, you can get by with 2 and still meet the rest requirement by having during the cruise phase 1 pilot going to the crew rest area, and essentially having only 1 pilot during cruise. And one of the advantage or one element that we want to get from the research from autonomy is workload reduction. How can we reduce the workload of the flight crew by automating some procedure and some maneuver that the pilot will do on the aircraft? And also because we're talking about single pilot operation, if there is a pilot incapacitation, we want to ensure that the aircraft is able to perform continued safe flight and landing even with the pilot incapacitated. So that's an area of research where the aircraft will need to, by itself, be able to negotiate airspace, event, weather, to be able to complete safely a mission after pilot incapacitation. Another area that is of interest for application to Part 25 aircraft is to increase efficiency and reduce emission. So getting improvement in performance by essentially having a perfect or automated flight so that you are always operating with the most efficient routing, for example. Pilot augmentation and decision making. So because the whole concept of autonomy is to be able to fly the aircraft by itself, the data is available. So one element that could be done is to provide that same choice to the flight crew so that they can better plan a diversion, for example, because you now have the capability to compute how to resolve a mission. So it's a task support system. And also with regard to data processing, mostly in advanced aerospace where more information are available. A third area that is a potential application for large aircraft is for reduced scale model testing. So if you want to understand better new concept like flying wings, you can fly reduced scale model, and this is where you will have improvement in aerodynamics and controls law and better understand new concept for new shape of aircraft. And directly, the concept for autonomy and advancement in autonomy also provide resilience for loss of communication when the aircraft is operated from the ground, for example. With regard to the research and development, autonomy, challenge, and needs for that industry, the most important one is the development of CONOPS, concept of operation and regulation. Having research, whether it's research center, academia, and mostly regulator eventually, develop perspective on possible operational regulation. What type of mission can you undertake in reduced crew operation, single pilot operation, and what equipage do you need to perform those missions? Very important to understand and to research. Today, there is not really any regulation that we can foresee. IASC the European certification agency is very active in creating projects, but there is no real orientation about how can you operate aircraft with those new operational concepts. That may come in 2030, 2040, but it's there down the road, and that's a good, that's an important element to develop the human-centered definition and test of the CONOPS. Relationship between human and automation, because now you have the capability to introduce common level automation. You need to look at the interaction between the human and the automated agent. How can you delegate tasks? When can you delegate tasks? How can you prevent conflict? So preventing antagonistic action between the human agent and the automated agent if the same plan is not followed. How do you transfer those plan and intent? And also one element is the evolution of pilot role, going from direct control to a more supervisory type of involvement in the flight. And at last, communication and explainability. So how do the automated system, how the element that can create autonomy can communicate with the pilot, and how can we ensure that there is a deterministic behavior in front of uncertainty when there is events that are unplanned during the flight. And for Part 25 aircraft to be able to certify, this is a very important element to be able to prove to the certification agency that the aircraft will be as safe as they are today, and that all the standards are respected. So obviously this is a long journey that we will need to take. As I've mentioned, it's probably something that we will begin to see 2030 plus 2040, but it will come very soon. So thank you.
All right, thank you. All right, thank you, CASI, for having us for this, giving this opportunity to talk about autonomy. So I'm the only academic representative on the panel, so I get to do a PowerPoint like all the others, but I just add references and citation at the bottom. So that's a major difference.
And the students get an exam afterwards, right?
Oh yeah, they will. Oh, no, it will be a good
Like
question.
1,000 feet exam.
All right. So we have over the years, automation has improved aviation safety. So that's a survey done by Airbus from 1958 up to 2022 of aircraft accidents. And what we see is that for each new aircraft generation, we were able to reduce by about a tenfold the rate of accident from generation to a generation. We also have 30 years of good human factors research on the involvement and the interaction with automation. So what we've seen is that automation improved safety, but it also introduced new problems. It had introduced automation complacency, black box phenomenon, not understanding what the automation is doing, loss of situation awareness, so not understanding what is happening, and automation surprise, so being startle effect when the automation disengage and the pilot needs to re-engage. The recent 737 MAX accidents, plural, show the consequences of a lack of human factors consideration when having to face an automation failure as a result of a technological failure. Automation is a spectrum going from basic automation for improvement up to full autonomy. And so this is what we define as level of automation. So the European Certification Authority, IASA, has brought forward their second version this summer for their framework to be able to certify artificial intelligence on the flight deck. And as part of that framework, which is, I guess, very much influential, they broke down the automation into 6 levels, paving the way to full autonomy. What you see here is that the most challenging aspects of the automation design for aviation are in the intermediary levels, where the pilot, or human, has to interact with a more capable automation, paving the way to autonomy. So this is where all the challenge resides. Whenever we'll get to full autonomy, so the last level, I will most likely lose my job, because at this point, the pilot's involvement is no longer required. But before going there, we have a lot of work to do. And so that's the reason why we're all here on stage talking about human-centric autonomy, is also because the IASA framework put forward strong requirement for human factors involvement throughout the process to be able to account for the changing role of the pilot when facing autonomy, and the need for bi-directional communication between the pilot and the autonomous system. So I will focus more on the human AI teaming, or human autonomy teaming, where all the excitement resides at the moment. So IASA spelled it out into two sub-levels. Human autonomy teaming is a major change to the way we work with automation compared to previous human factors research. It considers the autonomous system as a teammate and not as a tool. And considering that as a teammate means that they both work toward a common goal, so both being the autonomous system and the pilot. The cooperation perspective, in that case, the autonomous system helped the user to accomplish its goal. In this case, the pilot remains in full authority to be able to give the script that the autonomous system needs to follow. The collaboration is where the game changes. In that case, the autonomous system is considered as a teammate on par with the human pilot. They both work, the autonomous and the pilot, toward a common goal. In this case, bidirectional communication, so from the pilot to the AI, from the AI to the pilot, is of utmost importance to be able to understand each other's intention, what the AI is doing, what the pilot is doing, and vice versa. And it will also require major changes in how we do human factors certification. So let's have a look at autonomy. O'Neill and his colleague recently did a survey of empirical study that involved human and somewhat autonomous system to be able to see whether we are able to see any findings. As I mentioned, we have over 30 years of good research on automation, but it's not clear to what extent it applies to autonomy. Out of the 76 studies that they found, they were all based on simulation. None were on the field. Majority of those were from the military domain, essentially the UAS, Predator, and the drone systems. What they found, based on that, out of that number, is that more autonomy tends to give better overall performance in terms of trust, confidence, and intention to use the system. Transparency, meaning that the system tells the pilot what it is doing, also led to positive outcome. But they figure out that it also induced misplaced complacency, where the user tends to give it up to the system to be able to do a task, and have workload management problem whenever a handover is required. Finally, communication. We know that bidirectional communication is of utmost importance in autonomous system, for the system to know what the pilot wants to do and for the pilot to know what the system is doing. Yet, very little is known as to what to communicate, when, and under which media. So this is most likely still an open research question that we need to investigate. Similarly, recent report by the Science Institute were able to survey the state of knowledge on human AI and human autonomy interaction. And of most interest is that they were able to break down this level of autonomy grid into the 3 steps of human information processing, from perception to decision to action. And they found out that the major improvement were to automate the perception level. So highlight information, queuing, information filtering, this is where we have the most benefit. As for the other steps, whenever you try to automate decision making or action making, this is where you fall out with the out of the loop syndrome, a black box phenomenon, and loss of situation awareness. When to give control? Adaptable, meaning the pilot decides when to give the control versus adaptive, where the system decides when to take over the autonomy system. So what we found is that human-given control tends to be better than system-decided. But again, very little research is done on that topic. And the granularity of control is the level of detail that needs to be given to the autonomous system. A promising aspect is the playbook control. So in the playbook, in that case, the pilot is like a football coach that calls a play at the right time to give to the system, at which point the system can execute this prescript play. And what we found is that the playbook control tends to give positive outcomes even in unpredictable situation and for good workload management. So that calls over the contract method that the NRC has put forward to be able to control their autonomous system. And finally, there's a clear lack of methods, design and engineering methods, to be able to investigate the fine-grained interaction between the human or user and an automated system. Really, some methods exist, but we have a lack of direction to be able to use it in new research project. And so that's really a call for action for future work to come. All right, thank you.
All right, good day. So I'm Yann Moffett. I'm part of the Director of Technical Airworthiness and Engineering Support. So we're basically an organization that's analogous to Transport Canada Civil Aviation, where we have a similar role where we certify aircraft, but specifically for Department of National Defense aircraft. We're involved in this discussion primarily got invited because we're sponsoring the NRC's activity that were briefed by Duff. Because fundamentally, we see these topics as being emerging, and we're trying to get smart and trying to figure out how we're going to address that from a certification perspective. So today, the main goal of my brief is basically I've identified what I consider to be the three fundamental challenges that we have to resolve from a certification perspective. And it's quite interesting because although we prepared for this, there's a lot of common themes that are coming back. Having the benefit of being the last, I've noted that at least I don't feel like I'm off the rail. So basically, challenge number one, regulation. Obviously, this was brought up quite a bit by Benoit as well. I see this challenge as being similar to the challenges that we have with unmanned aerial aircraft systems. D&D is in the process of procuring some of those, so we know that this is a problem that we're gonna face soon. So regulation from two main perspectives. So aircraft operating rules. So again, Benoit mentioned the need for a concept of operation. Like thinking about a fully autonomous system, how are these systems gonna basically interface with other aircraft? How we're gonna maintain safe separation? How air traffic control is gonna interact with these systems? So RTCA DO 397 identifies some of those gaps for UAS, but I think they're largely applicable to any autonomous system. And a little bit analogous to instrument flight rules and visual flight rules, NASA has come up with this concept of digital flight rules, which is a new concept that might be the solution to that in terms of how we manage the airspace. So attached with that is the need to identify the required equipage for the autonomous systems, which feeds into the aircraft certification after that. For now, there's interim solutions or ways to operate, like Jeremy was mentioning, special flight operations. In Department of National Defense, we have a little bit of a similar process to grant flight permits, but this works in the context of smaller or just one-of test operations, but it's, you know, in the longer term, we for sure need to have operating rules put in place. And of course, that's not something that DTAES can certainly be engaged, but that's not something that we can resolve on our own. And then the second part of the regulation is having a proper certification basis for the autonomous system. So we've talked about Part 25 or Part 29 aircraft. Those have a fundamental assumption that an operator or pilot is in the loop. You know, in fact, there's a lot of requirements that relate to them. So this just shows that there's a need for a specific cert basis. For UASs, there's a NATO STANAG, so the North Atlantic Treaty Organization. This is a possible certification basis that can be used for large UAS. However, you know, also that assumes that there's an operator in a ground control station. So it's not fully autonomous in the sense that there's still supervision that takes place. So that's challenge number one. You know, airspace rules and certification basis. The second large challenge that, from my perspective, and we've touched on that from a number of perspectives, it is about identifying those autonomy functions and the analysis tied to that. I mean, I've only put one slide there as a one challenge, but really this could have been broken down into multiple challenges. But really, what do we mean by autonomy? So identifying more precisely what those autonomy functions are is necessary in order to assign those functions at the aircraft and at the system level. And this is all tied as well to the identification of possible failure modes. That's part of any classic design. Now, attached to those autonomy functions is the need to have means of compliance for the minimum operational performance standards. So some already exist, perhaps. A lot of MOPs actually also have an assumption that an operator is in the cockpit, you know, whether it's in the form of warnings. You know, it assumes that the pilot is going to take action from that. But there's also probably a need to identify or develop new autonomy-centric operational performance standards. The next item is really, we've touched a lot on human factor aspect of this. Before we reach full automation, the human is going to play a different role. So this is a challenge in and of itself. And talking about CVLAD, the project with NRC, there's a lot of work that's being done and trying to understand that and how we're going to cope with that from a human factor perspective. And so the next topic, intuitively, you know, abnormal conditions. How do we deal with any failures or external events that are not really predictable? I guess you can model that, but I guess for me the challenge is how do we, while keeping in mind that there's a human system teaming, how do we make sure that this analysis is complete and systematic? I'm not sure. It's certainly a complex system design, but for that reason, I think for the foreseeable future, an operator is going to be, it certainly appears essential from our perspective. And then the last challenge, and we've alluded to that quite a bit, we've talked about artificial intelligence in this panel. So I separate this one from the autonomy topic, thinking historically there's a lot of technologies that initially there was no guidance from a certification perspective. I'm thinking, like on the slide here, multi-core processors, or whether it's object-oriented or model-based development. Initially there was no guidance for that. So generally speaking, in the case of those topics I just mentioned, there is guidance on how to deal. Usually it involves using some constraints on the technology so that it's more bounded. For sure, an enabling technology for autonomy is AI. And DTAES, we're keeping an eye on the multiple organizations that are working on that. Most promising are probably the SAE G34 that's coming up with basically the AI trustworthiness concept, which is quite interesting. But we're hoping that this is going to provide a way for us regulators to certify that technology. Just to recap, having airspace and aircraft rules followed by means of compliance and guidance for regulators are what seem to be the key topic that need to be addressed. And I've kept it separate. So the challenge number 3 here, I believe that autonomy would benefit from AI for certain functions, perhaps. If we speak more specifically, like we mentioned, perception, perhaps, and this concept of decision making. But I believe that a higher level of autonomy is possible without actually using AI. But they're related but separate challenges. That's all I have. Thank you.
All right. So, well, I mean, all of your topics raise a significant number of questions and ideas. So let's go through some of those. So maybe as a first challenge question, and I'll just throw this out there. What are your perspectives on current taxonomies developed internationally? So the levels of functionality from piloted to fully autonomous, as well as the definitions of autonomy and artificial intelligence. What are your perspectives on those, I guess you could say, definitions? Start. Anyone would like to take a shot at that?
No, I like to talk. So I think like we saw IASC's model up here. ASTM has a model. I mean, within NRC, we developed our own to sort of help communication. I think there's sort of some fundamental requirements as we look to adopt a taxonomy. One is that it's a spectrum, right? It goes from J3 Cub to that eventual full autonomous system where the pilot wakes up and goes, gee, I want to have a pizza delivered, and it all happens automatically, and then they go back to bed. So it's a spectrum. But I also think that until we get to that mythological full autonomy space, we always need to identify the operational design domain. So each of those levels of autonomy have a specific regime of flight and environmental operational conditions within which the autonomous system can function and not function. It's like we all talked about how we break it up. It came out in every presentation where there's elements of phases of flight where the autonomy system would be applied. And so I think that's a sort of a key facet to how you define it. In terms of numbers and how we break it down, I think they're very similar ways of addressing it. I think IASC has done a masterful job. I think that's a great way to look at it personally.
Any other perspective?
Automation is being able to, for a system, to execute or to do someone else's job or task. Autonomy is to be able to show some kind of decision-making ability. And so the frontier from automation to autonomy will change with time as we get more and more advanced into the system. So for me, autonomy is decision-making and also being able to work in unexpected situation that were beyond what it was initially developed for. So, and I think this is the frontier that we're at now.
Right. So I guess from my perspective, any functions that are assigned to an aircraft design is become automated. So I believe that automation. It's not clear what becomes. So the moment that you identify a function that you want your system to do, for me that becomes automation. So autonomy is once everything becomes automated. But there's a recognition that for sure there's a layer at some point that becomes more decisional and difficult to implement in the system.
What about industry perspective?
What is interesting is that you could define also taxonomy based on, is it within the engineering realm or is it something completely new? Because typically when we look at the taxonomy going from pilot as full control to automation as full control, we're looking at the boundary of the engineering development. And we're not looking at other events that are not known or that haven't happened yet. So this could be one element where there is kind of a split between what we can consider within the engineering realm and then the uncertainty.
What about enterprise?
I think I would broadly agree with a lot of the sentiments that have been shared already. I especially agree with what Philippe mentioned in terms of autonomy coming in when you talk about decisions, and then automation being kind of a lower level capability. I mean, I think something very practically that is just purely observational, it's not by any means a rigorous taxonomy, would be that it would be kind of silly to say like you have an autonomous control law, or to refer to linear controls as being autonomous. Like we can talk about automating control laws for an aircraft, but it's kind of weird to talk about it in an autonomous fashion. And so at least internally within Ribbit, when we think about autonomy, it tends to come back to discussions around states and discrete decisions as opposed to continuous systems. So when we think about the continuous behavior of a control law, the continuous behavior of trajectory planning, those things we would lump into automation. And then when we think about the way that a system transitions from one discrete or finite state to another one, even if there's some blending in between, that's kind of more of an autonomous capability. It's not a very rigorous way of looking at it, but it is where all of the tricky questions we've had to deal with tend to come into play.
So that sort of technology definition, I mean, it's not definite yet. I think there's still a lot of flow and still a lot of interpretation. Perhaps we can move on to a Canadian perspective. So, Canada has many aeronautical challenges. What are some of the unique Canadian flight autonomy perspectives? I have a list here, but I'm not going to say what they are. So what do you guys feel are some of the specifically Canadian challenges? Let's just try and identify those. Anyone can start.
I mean, we have a unique Canadian opportunity with the fact that we have, a strong aviation ecosystem already established, with academics, research center and industry being able to work, so closely together. And I think that's, a major advantage compared to other states or nation states that don't have maybe such, so well integrated research and call into action. Yeah.
And that ecosystem, the fact that it's relatively small, should be great to be able to have more relationship. Like we know each other. We know the research center, the industry, the enterprise that are in that situation. And I think we have a relatively close relationship with Transport Canada generally. So this is a unique position, like the fact that we don't have hundreds of industries that are in big administrative cadre where the regulation is done. This should give us that capability for agility and being able to cooperate much more between us.
Yeah, actually, maybe just to piggyback off of that a little bit, I guess the two things that certainly we've seen at Ribbit is the closeness of that environment makes a big difference. There are companies in the States, for instance, working with the FAA that talk about how huge of a bureaucracy it is. And in Canada, you literally pick up the phone, you call your Ontario region person, and you're like, hey, I have a question about this, right? You may not get a very helpful answer, but you at least get an answer. So that closeness of the environment is certainly a big advantage. I think the other thing I'll say about that is when you have fewer players involved, or at least more nimble players involved, it's a lot easier to get started. And so if you look at some of the drone projects that Amazon and Wang and others in the States have done, a lot of them actually came to Canada first to get their approvals and then went back to the States to really start scaling. And that's where I would say the second concern is even though I think we have an advantage in terms of being able to pull together players and get started going from 0 to 1, I do think there's a challenge in terms of scaling. And perhaps with the creation of INSAT and other programs, they're going to bridge that gap from initial conceptualization and demonstration to being able to operate at scale or change things operating at scale. I think that's where the future challenges and kind of open questions lie for us.
I mean, just a quick note. Coming from the military, I know Canadians are known to just make it work. So I think that echoes what you said.
It's interesting. Like, I agree with everything that's been said for sure. I mean, one of the things that occurs to me is this is a big, challenging problem space, especially if you look at it from the regulatory angle, and it's going to require collaboration and cooperation between different regulatory agencies around the world in order to make it work. And I think that we have unique opportunities. We also have unique application space. Jeremy articulated it very well in his presentation. But I think we also have there's Canadian obligations, things that Canada needs to have a unique look at. And so in our regulations, in the civil regulations, we have icing requirements that are unique to Canada, cold weather requirements because of our environment, obviously, that we're now getting to experience as the season changes. From an autonomy standpoint and how systems are developed and introduced commercially is going to have a national social perspective. And so I think that we have an obligation to have sufficient knowledge and contribution as well within that space to have a Canadian unique contribution, of course, and hopefully significant contribution within the ecosystem, but also from a regulatory standpoint. Trust is a big one, right? Suitability for applications of the technology. We've talked a little bit about Part 29, 27, 25 type applications, a little bit on urban air mobility, but flying taxis in Canada versus flying taxis in the United States, in LA or New York versus Tokyo versus Dubai, there's going to be a national perspective to these things that need to be considered as well. Mm-hmm. So I think that's a different perspective, maybe, or a different angle of the question.
You already answered my second question about scaling, so maybe a regulatory question. We've started to look at regulation of advanced technologies such as autonomy systems, artificial intelligence. I mean, we've started, and DND is implicated and starting to look at those particular perspectives. For example, I guess you've listed some of the challenges. I guess we were talking about non-deterministic systems. Are we ready to certify those type of systems? Should we be using that type of terminology when we look at these type of technologies? What is your perspective in the sort of the certification regulation of this technology? How are we going to do it? How are we eventually going to certify it?
I can try to speak to that a little bit. I mean, I haven't done a lot of sort of research recently on specific terminology. From my perspective, non-determinism is not a term that inspire trust. But at the same time, I don't think that it puts the finger exactly on what the issue is. I think from a regulatory perspective, to me, it's more about ensuring that the functions that are assigned to the system are correct and they meet the intended function. But to me, it's more about explainability of that implementation and making sure we can, from a technical perspective, trust that it's going to do what it's supposed to do, right? Linking back to the previous sort of question, I mean, DTAES is a pretty small organization, so technically what we normally do is leverage the guidance from other organizations. Which is why I mentioned that we're keeping an eye on the work that's being done by on AI. Realistically, we're not a kind of organization that could come up with this guidance, right? So we typically leverage, but that also makes it a strength for us, is that we're not bound to our own specific set of guidance. In DTAES, we obviously have our awareness program, but we can leverage whether it's FAA or IASC's guidance. We can use whatever makes sense. So we have a lot of flexibility from that perspective. So, but are we ready to deal with that right now? No, and that's why we're partner with NRC trying to understand moving forward.
Any enterprise or industry perspectives on that? Meaning, obviously you have product ideas and things you want to develop. When will, the idea of when we will be able to certify it is critical to getting those products out.
Absolutely.
So,
and Philippe provided a great graph with regard to the reduction in number of accidents because we are improving the automation, but we are also improving the process. And I'm talking part 25 here, probably it's similar for part 29. But whatever technology we introduce, technology like autonomy or part of autonomy that could be AI, will need to be demonstrated to be safer than the current baseline. And the achievement of decreasing this curve is about also more process. And human factor for flight deck certification, we certified the flight deck. One of the big rule is 1302 for the equipment used by the crew. And we have now much more requirement about the process of creating requirement, RP 4754. So if we compare an aircraft that was certified 15 years ago and an aircraft that is currently certified, the process is much more rigorous. So to bring AI in the aircraft and be able to use it operationally for significant tasks will require to meet that safety standard, which is a very big endeavor in itself.
With regards to the accident rate chart, I guess my question on this is, we reduced the numbers, but the types of accidents we have seems to be the same.
Oh.
So will this technology enable us to start reducing not just the numbers, but the similarity in the types of accidents we see? Structural failures, human factors issues, et cetera, et cetera, et cetera.
Yeah. So definitely the type of accident changed with aircraft generation and technology. We went from structural failures, then we went into terrain collision or CFIT or loss of control. But then this is how the new technology were introduced to have TCAS to be able to avoid traffic. We have terrain awareness warning system to be able to avoid collision into the terrain. We have fly-by-wire technology that is able to avoid loss of control, such that most of the system-related failure account for a small margin of fatal aircraft accident. Now today, the primary cause of fatal aircraft accident is human error. That's what happened in the last 10 to 20 years. And so now the frontier is to try to reduce that human error or improve human reliability. And being able to introduce decision support system or system that can augment the pilot capability for decision making, monitoring, and especially reaction to startle effect would be a major safety improvement that will be able to address these last few catastrophic events that we've seen in the last decade, really.
And in each generation, you start a bit higher and then you decrease, and you are on an asymptote. You are at a plateau. So essentially, each generation of category of accident has reached that type of plateau, and with more task support system, then essentially what we are trying to do is we're starting the next generation, and we will need to address the challenge of that next generation of category of accident that is lower than where we are today, but that involve different challenge.
Interesting. Roles. We have a number of students here who won't let us out of this room unless you give them jobs. I guess there's sort of a duality in this sort of question. How will roles of the human change as we introduce this technology? So the user, you could say the pilot, and then potentially students, people who are going to develop this technology. Could you speak on those two fronts?
I can maybe start with the pilot, and I will let you like for student. So for pilots, the role will, and it has started probably since the introduction of the first FMS on an aircraft. So there is this shift toward more supervisory control. So like it or not, the pilot of today will not be able probably to understand some type of failure on board of the aircraft that a pilot from a generation where there were engine failure that were much more prevalent, much more system failure. So it's quite different today, where most of a pilot career, you will not have an engine failure. You will be flying within this realm of supervisory control, where you engage the autopilot at 400 feet and you maybe auto-land the aircraft. And this has also an effect on the erosion of skills, because the only time that you're faced with really flying the aircraft, controlling the aircraft, will be in the simulator. So with regard to automation and also the enablers of autonomy, Gamma, they have a very great citation which say that the backup to automation cannot be or very advanced automation cannot be the pilot. It needs to be automation. So you need to create systems that are safe enough that when a system stop to function, you don't give back the control of the aircraft to a human in the worst possible situation. So the interface will need to adapt for that kind of reality.
From a student perspective, I've read recently 85% of use cases where they tried to develop AI for business setting were failures, meaning that they did not achieve the business objective, and they did not reach the business goals. That's a big number of failure cases, really. And so the role that students will have to do, and the role that this industry will have to develop, is try to come up with the human-centric perspective, i.e., what problem do we want to solve, and how can we work to be able to solve it, definitely. Having a technology-driven perspective most likely will miss the point of the involvement of the pilot and its user. And so I think this is a new skill that needs to be developed for our next generation of students, really, that we can leverage to be able to have increase the number of successful AI cases in the industry.
He said it, right? I didn't say anything about so we're running a bit long, but I did want to give the audience a little bit of chance to ask a few questions. So how about we get those interesting questions that you've all prepared. Do we have a mic out there to capture that voice.
I was told to use a mic, but I don't need a mic. I have a gym voice. I have two questions, actually. One, because you're going automated and autonomous, what are your strengths or confidence in hackability of your system? Because that's definitely the new age of the world. And the second question I have, completely different, kind of goes towards with the Northern Ontario Canadian problem. What are your potential success rates you think that the automated planes will be able to fly during the no-fly times in Northern Canada?
I'll take a stab on that one.
Okay.
So I think the first question was around challenges with cybersecurity. That is absolutely one of the new risks and failure modes that is evident with this. I don't think there's simple answers to that, given that it's like we're currently in an arms race in many cybersecurity frontiers. There are various precautions we take for data in storage, data in transit, but there's also even electromechanical aspects to this too. Of even if you've built in cybersecurity protection measures in the software, you can still jam these planes, and there are those kinds of challenges. So those are things we're well aware of. I don't have an answer for you right now, but those are definitely big challenges. The second question, in terms of good weather days, especially across Canada. So we actually spent some time benchmarking historical METAR and TAF data, so that's kind of aviation weather data, if you will, across the country. The challenges vary depending on regions. So on the east coast of Canada, most of the challenges with bad weather days arise due to fog and lack of visual meteorological conditions. And because some of the approaches into the runways require a visual approach, that ends up making those flights not feasible. That's actually an area where autonomy could be beneficial, in the sense that if you're not flying based on visual flight rules, that would actually improve your number of good weather days. But in other parts of Canada, it's different. So Ontario and Manitoba, you're looking at about 15 to 20% of any given year's bad weather days, depending on the aircraft you're looking at as well. And the worst times of year tend to be in the transition season, so fall or spring. You go into the far north, you have more icing issues and very cold weather issues, so it varies. But the one thing I will say is that there are so few operators that are serving so many of these destinations that the number of flights that are available and the amount of market competition that's present makes it very appealing for entry into those markets. If you just took the price of air freight and tacked it on to the price of food in a city, you'd expect prices in the north to be maybe 20 or 30% higher, but they're not. They're 3 times higher, 7 times higher. And we believe, and this is backed by a certain amount of data and interviews, that's also driven by market effects. So even with the challenges with operational cadence that could arise in certain regions, the fact that it's just an underserved market makes it very appealing for entry regardless.
I can maybe add just on the first question, just to add quickly on cybersecurity, I can tell you, of course, this is on a case-by-case basis, but for sure this is an item that D&D takes particularly care about. And I just wanted to mention that we do have a specialty that we call cybersecurity within our certification organization, and there's a whole slew of assessments that would need to be done on the specific design, which is tied to the system safety assessment. But yeah, so just that would be something that would be addressed. That's for sure.
Maybe we could take a student question. I know you. No. I already know that. Yeah.
especially
I can start. So I'll share our perspective at Ribbit, which is a little bit different than the Part 25 kind of big airplane world. But we're almost exclusively focused on Part 23 aircraft. So, relatively few seats, small planes, the kinds that you would find at a flight club or a flight school, and certainly the kinds you would expect in bush flying. In reality, today at least, a lot of pilots that are looking to move on to, say, Air Canada or WestJet, use the Part 23 world to build ours. And so there is a fairly regular stream of pilots entering that world and doing this kind of flying. Where the challenges become a bit more unique is, bush flying in Baffin Island is a very different, experience than doing flying in Ottawa, at least most days. So as a result of that, there are a lot of these. There is definitely a challenge in terms of being able to get a kind of consistent stream of pilots with that background, but also kind of a relevant background to each specific operational use case. In our case, I would say we're less concerned because what we found is that at least the test pilots we've been working with and the environment we're working with, people tend to come from either a recreational background. In a couple cases we've seen, like we have one test pilot who started in the Part 25 world and is now kind of transitioning back to Part 23. But I would say we're a little bit less concerned about it, but certainly longer term, as we get further and further to that far side of the spectrum, where now potentially autonomy is taking more and more of the crew resource management workload, that'll become definitely a big issue. I would say as well, just as an interesting figure, for every, or I should say, for the 200 hours of flights we've done on the physical aircraft, we've done about 7,000 hours of flights in simulation. And that's, supervised flights, I guess, to some extent. But that ability to have high fidelity simulation is something that we think will be an important part of that transition.
That ratio is the same for us, actually, in terms of our flight test versus development. And if I could just jump on that, I think you have to look at the application of autonomy. What part are you flying passengers, et cetera. And I think like Yann talked a little bit about certification versus operational regulations. We need that discussion to mature to really be able to understand the training pipeline. But I'm a huge believer of what my fellow panelists has said. Supervision is a high-end skill set. And in the most complex applications, it's going to be a very rare person that has that capability. And don't confuse that with, the videos of research systems in development where, I wouldn't say necessarily trust is low. Trust in autonomy, this is a phrase that Brian uses all the time. Trust in autonomy is okay. Trust in autonomy programmers, maybe not so okay. So don't read too much into that. That's part of the development single string. There's all sorts of test risk there. But in terms of the actual applications, the ability to generate those pilots with high-end skills as we reduce their opportunity to build those skills has to be carefully considered as the regulations are formulated. And I think that's something we really have to get right, or it'll become a dead-end situation where we won't be able to deliver. It's a big challenge that needs to be considered.
Well, thank you for all your questions. Thank you for attending. As you've seen, this is a massive, wonderfully vast, wonderfully opportunistic, wonderfully opportune area to work in, to research, to study, and to get involved in. I'm sure I speak with everyone here, if perhaps through CASI, if you have questions or other comments that you'd like to make, you can just send them along, and we'll try and answer those later, maybe send you an email, that sort of thing. But I want to thank the panelists for attending. You've given us a perspective on the industry, the enterprise, the research, the regulation, and this I'm sure has informed everyone here. Again, thank you all for attending. Look forward to seeing all the young people involved in the industry, whether it be engineers, scientists, pilots, programmers. Excellent programmers, safety programmers. See you in the future. And to the industry, the military, we're very happy to have you here, happy to have you on board with all our programs. And we hope that you know, working with us will help inform your decisions in the future, and we'll see some of this really interesting technology flow through industry and the military. So thank you very much, and have a good conference. Thank you to CASI as well for hosting this session.